All right, welcome back. Long time no see. Today we're going to talk about instance-based learning. Instance-based learning is just about the simplest kind of machine learning there is. It comes in a number of different flavors. The first one we're going to look at is probably, you could consider it the oldest machine learning algorithm and certainly the simplest. It's the famous k-nearest neighbor algorithm. And then we're going to look at other forms of instance-based learning, and we're going to conclude with a look at collaborative filtering. Collaborative filtering is these days probably the most well-known application of instance-based learning, and it's what your second assignment is going to be about. You're going to develop a collaborative filtering system and apply it to the famous Netflix data. It's too late to win $1 million, but you might win the next one. As I mentioned, there was someone in this class who didn't know any machine learning before, and got interested in it and went on to be a member of one of the two top scoring teams. So. First of all, what is instance-based learning? And why is it so simple and potentially so fast? The idea in instance-based learning is to do as little work as you can at learning time. It's also known as lazy learning. Lazy learning and instance-based learning are not exactly the same thing, but at this point we can think of them as the same thing. The idea in instance-based learning is that what I'm going to do when I see the data is nothing. Right? If you think about it, that's the fastest algorithm you can possibly imagine, right? It's O of 0. You do nothing. You've never seen an O of 0 algorithm before, you're never going to see one again. This is the only O of 0 algorithm that you'll ever see. So what I do with my database of training examples, XIs and their corresponding classes is nothing. I just leave them there on the disk and hope for the best, right? This is like not studying for your class and waiting till the final comes, and then when the final comes, of course, at that point you scramble, right? You didn't study, you don't know anything, so what do? How do you quickly figure out what the answer should be, right? Well, the idea in nearest neighbor, as the name implies, is that when a new query instance comes along, say I have a new patient, and I want to decide whether this patient has tuberculosis or whatever, what do? At that point, I just quickly scan through my database and try to find the closest patient in terms of their symptoms and tests to the one that I'm seeing now. Okay? And then whatever the prediction for that item was, I make for the new item. Right? If you think about it, this is not a bad heuristic, right? If you find two patients whose records are pretty similar, there's a good chance that the diagnosis will be the same. This can actually work surprisingly well. Okay? So if my nearest neighbor is xn, all I do is I estimate f of xq. Notice the hat here that says it's an estimate as f of xn. Okay, very, very simple thing. This algorithm as it is doesn't always work that well. There's one very simple change that makes it work a lot better, and in fact makes it competitive with a lot of much more sophisticated algorithms. And that is simply to just use the k nearest neighbors instead of the single nearest one. Okay? So what you do, again, at learning time you don't do anything. It's still O of 0. What happens now when you see a query is that you find the k nearest neighbors, like say the 3 or the 5 nearest neighbors. Okay? Each one of those has a class, and then you just vote. If one class is the class of 3 of the 5 nearest neighbors and one is the class of 2, well, the first one wins. Okay? If what we have is a regression problem, right? We're trying to predict a continuous variable instead of a discrete one, then what might we do? Right? I find my 5 nearest neighbors, I just treat 5 numbers, and I want to predict a new number for this example. What do?
You already have some formula based on the regression.
Yeah, well, you're getting way too fancy for us simpletons here, right? What's an even simpler thing that you can do, right? I want to predict how much you buy from my catalog, right? And I know that they each bought, a certain amount of dollars, and they're the 4 closest neighbors to you. So what can I predict for you?
Check the distance from the...
Even that is still too fancy, right? You've almost covered the whole lecture right there, right? Yes, we could weight them by distance, right? The closest ones probably mean more, right? But if I just tell you, your 5 nearest neighbors have these values, and what would I predict for you?
Mean?
Yeah, just the mean, right? Just average them, right? That's a perfectly sensible thing to do. Now, the average could be weighted, and we'll talk a little bit about that later, right? But the basic idea is that for discrete problems, k nearest neighbor just votes, and for continuous problems, it just averages, right? Fairly simple, okay? So, as with all methods, it's good to bear in mind what the advantages and disadvantages of this are, right? So, what are the advantages of nearest neighbor methods and instance-based learning in general? Well, obviously, one key advantage is that the training is very fast. Truth in advertising, once we get to some of the fancier versions of this, that speed at training time naturally can disappear. But at least in the basic version, the things at training time can take no time. Another important advantage, which is a little more subtle, is the following, is that if you want to learn a very complex target function, well, this can be very hard. But with these methods, you could actually learn a very complex target function very easily. Because what happens is that when you memorize those examples and then you find the nearest ones at test time, implicitly you could be learning a very complex function. We will illustrate, how this happens and look at it in a little bit more detail, in a while. But for the moment, keep that in mind. Okay. Another thing that is sometimes an advantage compared to something like, say, a decision tree or a set of rules is that with these methods, or at least with the most basic version of them, you don't lose any information. But with the decision tree, once I form the decision tree, I don't have the training data anymore, and maybe I'll regret that. Maybe at some point I would wish to know what that point was. In nearest neighbor, I still have my whole database, right? So I haven't lost that information. Okay? So these are the advantages. Now, what are the disadvantages, right? Well, one prominent and obvious disadvantage is that this can be very slow at query time. And in fact, the more data you have, the slower it gets. Usually having more data is better because I can learn a better model, but here having a lot of data could really kill you. Let's say you're trying to control a robot in real time, right? And you have frames of their, past behavior. You don't have time to run through all of them. Compared to, say, a decision tree that's blindingly fast, this is a problem. Or, you're trying to play the stock market, then, you need a response in a fraction of a second or your competitors will beat you. Instance-based learning could be a problem for that. Okay? Another obvious disadvantage, which is actually not such a big one these days, is that, of course, this takes a lot of storage. A set of rules you can probably store quite efficiently. With this, you have to store all, the data that you've seen. In fact, when nearest neighbor was first invented, circa 1956, storage was a huge problem. In fact, this, for a long time, nearest neighbor was not considered practical because who could possibly have the storage to store even 1,000 examples, right? This was back when memory were like ferrite cores, right? These little, magnets, basically. Right? And over time, sometimes memory is the bottleneck, sometimes memory is not the bottleneck. Actually, these days, memory is not the bottleneck, right? Disk is cheap. You can store all that stuff, no problem. Okay? But finally, here's the least obvious and actually the most important of these problems, is that nearest neighbor methods are easily fooled by irrelevant attributes. Let's say I have 1,000 attributes of each, person, most of which are totally irrelevant. There's a few there that are really relevant. And if I measured, my similarity using only those, I'd be in good shape. But the signal from those is swamped by the noise from all the irrelevant ones. And now I have a serious problem. Okay? Notice that decision trees and rule sets, for example, are very good at dealing with this problem, right? This is what they do. They find the relevant features and throw out the others. Here we're not doing that. Okay? Now, of course, all these problems are well known and have been, well appreciated for a long time. So there are solutions to all of them. Okay? Nevertheless, even after we incorporate those solutions, these methods are still not the best ones in these dimensions compared to, say, some of the others that we've seen. Okay? So it's good to bear these things in mind. Any questions so far? All right. So, well, there's one very big thing here that I didn't talk about yet, right? So, sure, we store examples and then at query time we find the closest one. Well, what exactly does closest mean, right? How do I measure that two examples are similar? Clearly, the behavior of this algorithm is going to depend a lot on your definition of similarity, right? Well, now your definition of similarity could be anything from extremely simple to very, very complicated. In fact, there's this whole area called case-based reasoning where your similarity measure is a huge program with subroutine calls and who knows what. Fortunately, for a lot of applications, just about the simplest measures that you can imagine actually work quite well. In particular, let's say that all your features are numeric, right? They're all numbers, right? What might you use as a distance measure? What is the first thing that comes to your mind?
Sum of the distances to each of them.
Yeah, so that is what's called Manhattan distance. Right, just the sum of the distances along each of the features. Okay. Or you can just use Euclidean distance, right? The straight line distance between the 2 points in hyperspace, right? Both simple, both widely used. More generally, you can use what's called an LN norm. LN norm means that you take for each dimension, you take the absolute, to compute the difference between two examples, you go to each dimension, you compute the difference between the examples along that dimension, take its absolute value, raise to the nth power, and then you sum along all the dimensions and you take the nth root. Okay? So Euclidean distance is the special case of this when n is what? 2, right? And Manhattan distance is the special case when n is?
1.
1, exactly, right? Because you're not raising to anything, you're just taking the sum of the absolute values. Okay? But, I could use other n's. The most popular ones are indeed 1 and 2. You know what the third most popular one is? Anybody care to guess?
3.
No, yes, this was a trick question. The most popular one is infinity. What is the L infinity norm? Sounds like a weird thing at first, right? What's L infinity? What happens when you raise the distance along each dimension to infinity, sum them all, and then take the infinite root? You just get the maximum. Right? Because as you raise things to higher powers, the larger ones dominate more and more. Right? So if you raise it to infinity, the larger one basically sums out all the others. So L infinity norm is just a fancy way of saying ignore all dimensions except the one with the biggest difference. And that's the one that's going to be your distance. For some applications, that's actually what makes sense. Okay? But the main point here is simple measures often work quite well. Now, so this is for numeric features. What about for symbolic features? What might you use as a distance measure between examples if you have symbolic features? What is the simplest thing that comes to mind? Right? How do you measure, the difference between 2-bit vectors? Right? Let's say my variables are just Boolean, right? So, what's a way to measure the difference between 2 Boolean vectors?
The Hamming distance is up there, but something like that. The number of bits that are different.
Yeah, exactly. Which is the Hamming distance, right? So the Hamming distance is just the number of bits along which they differ, right? Also known as overlap. So Hamming distance or overlap just means for each feature, if they're the same, right? And this applies to features with multiple values, right? If both of these things are red, then the distance is 0. If one is red and the other one is another color, well, then the distance is 1. Okay. Now, for a long time, this is all that people used with nearest neighbor. And it does not work, it's okay, but it does not work as well for symbolic domains as the kinds of things that we saw before. And so for a while there was this perception that, well, nearest neighbor algorithms are good if what you have is continuous variables. For discrete variables, they're not really competitive. And then much later, in the late 80s or something like that, early 90s, people actually figured out a very clever distance measure that you can use. And in fact, with that distance measure, nearest neighbor becomes competitive with many of these other methods. For things like, say, for example, predicting whether something is a promoter region in DNA or where splice junctions are and a lot of things like that. Okay? So what is this measure? It's a fiendishly clever thing. It's called a value difference measure. We call it measure and not metric because it's not a metric. It doesn't obey, the triangle inequality and things like that, or VDM for short. And the idea of this measure is the following, right? Let's suppose that my objects can come in multiple colors, red, green, and blue, right? The problem that we have is that what could possibly make red, more similar to green than to blue, right? With numbers, we don't have that problem, right? 2 is more similar to 3 than to 4. And that's why things like Euclidean distance make sense, right? But when what you have are just symbolic values, yes, they could be the same or they could be different, but there's no degrees of difference, right? If your object is red, any color that's not red looks equally different, right? And this is where people were stuck at for a long time. The idea in the value difference measure is the following, let's remember one important thing here, is that I'm not measuring this distance for its own sake. I'm measuring the distance for the sake of predicting the class, right? The whole point of deciding that two things are similar is that at the end of the day, because they're similar, they will have the same class, right? So what we want to do is we want to consider how similar, say, these colors are with respect to your class, with respect to whether you want to buy the car or not. Okay? So this is what we're going to do, right? So the value difference measure is still going to have this general form, except that instead of this absolute difference, I'm going to have this delta here. So let's think of two values of the same variable, val I and val j. And delta is going to be the following thing. It's going to be the sum over all my classes, so I do this for each class, of the difference between the probability of the class given the first value and the probability of the class given the second value. Right? Why is this a good thing to use? Is that now you see why red and green might be more similar than red and blue. Right? If people tend to buy a car when it's either red or green, right, then for purposes of predicting whether you'll buy the car, red and green are similar. If I switch red by green, the result will probably not be different. On the other hand, if people really buy red cars and don't buy blue cars, then those are very different. If now instead of red, in the example that I'm comparing with, I have blue, this is a big red flag, right? This might make a difference to the class. Okay? So all I do is I just compute these matrices of probability of the class given each value of each attribute, and then I just plug this into the usual distance measure. And now you can do, fancier things with this, and the full-blown VDM has more stuff in it, but this is the basic idea. If you just implement this, you will usually get much better results than Hamming distance. And on a good day, you'll beat some of these other methods that were actually designed for symbolic problems to start with. Okay? And of course, if in your problem you have a mixture of numeric and symbolic features, well, you just can use the corresponding component, in each dimension. For the symbolic features, you use one of, something like the VDM. For the numeric feature, you use something like Manhattan distance and so forth. Okay? Of course, this is just a starting point. In general, when you're using instance-based learning, this is probably one of the things that you focus on, is designing your distance measure. Okay? And again, this is where you want to put your knowledge of the domain. The kind of knowledge that you use here is what makes things similar versus what makes them dissimilar. And that's what you want to put in your distance measure. Okay? Any questions? All right. So, let us try to answer the following very important question. What does a set of when I do instance-based learning, right, I have a database of examples, right? And then when I, find the nearest example, with a distance measure and apply that, implicitly I'm representing some concept, right? Whenever we look at a new learning method, the first thing we try to understand is what is the representation, what can it do, what can it not do? And we haven't really done that here, right? And in fact, it's less obvious in this case than in the case of a decision tree, right? What does a big database of examples represent, right? What concept am I really learning, right? Think of this in terms of instance space, right? There's positive examples, there's negative examples, and we're trying to find the frontier between the two. And we saw that in the case, for example, of the decision tree, the frontier between them was basically a bunch of, axis parallel planes, right? A bunch of hyperplanes pointing in one direction or another. What is that frontier going to be in our case, right? And this is also going to help us to understand why these methods, despite being so simple, can be so powerful. So here's a simple example. Let's suppose that my instance space is the plane, right? Here it is. And think of it as the surface of a pond. Right? It's flat, there's nothing happening. And then my query xq is a little pebble that I drop into the pond. Okay? So poof, the pebble falls into the pond and you get this ripple, right? It's a widening circle, right? And already in the pond, let's say this is a Zen garden or something like that, right? There's other pebbles sticking out, right? Some of the pebbles are labeled positive and some of them are labeled negative, right? So in this, pond scenario, what is the class prediction for the query going to be? It's the class of the first other pebble that my ripple hits, right? Like, for example, in this case here, right, the ripple starts from xq, and then the first thing that it reaches is this plus here. And at that point, we go oh, you're the nearest example. Okay? I'm assuming, by the way, we're using Euclidean distance here, okay? The same ideas would apply with other distances, but, Euclidean is the most visually intuitive one, so we're going to focus on that. Okay? So, the first one that the ripple hit is the one that predicts the class. Okay? Well, but now let's turn this around, right? Which queries is this positive example going to be the winner for? Right? I can ask the question for each of these training instances, what region of instance space is it closest to, and therefore where the region where it's going to win and be the one that makes the prediction, right? We call that the Voronoi cell of that point. So the Voronoi cell of a point in space is the set of all points that are closest to that point than to any other. Okay? So these points are my training examples. I sprinkled them around space, right? There they are hanging. And now the Voronoi cell of a particular point is the region of space that's closer to that point than to any other. Okay? And here's a quick question. Suppose that I have a positive example here and I have a negative example there, right? What is the shape of the boundary between them going to be? Is it going to be a curve? Is it going to be a straight line? What is it going to be? Assuming we're using Euclidean distance.
Straight line. If there's just 2 points.
Exactly. It's the straight line that's equidistant from the 2 points, right? Because what is the frontier? The frontier is the set of points that are at the same distance from the 2 instances, right? And that forms a straight line. Okay? So the first thing that this tells us as a preview is that my frontier is actually again going to be a bunch of straight lines or hyperplanes in the general case. Okay? But these hyperplanes, unlike in decision trees, are not going to be axis parallel, right? So let's pursue this thought. So let's say that this is my training set, and here I'm not saying what the classes are because it doesn't matter, right? And what I've drawn here is the Voronoi cell of each one of these. So for example, the Voronoi cell of this one in the middle is this shape here, because for example, its boundary with respect to this guy is right here, right? Its boundary with respect to this guy is right here, and so forth. Okay? So any query point that falls in here is going to be classified by this guy, and so forth. Okay? So now I've defined this notion of Voronoi cell, and the Voronoi diagram is all the Voronoi cells of all the data points. Okay? And now here's my question to you. So if I have the Voronoi diagram, can you tell me what the region of positive class is going to be in terms of the Voronoi diagram? Let's say that this guy was positive, right? Then the points in the Voronoi cell of that example are going to be classified positive, right? And if this guy is negative, those points are going to be classified negative, right? So what is the definition of the positive region?
Union of all the regions.
Precisely. It's the union of all the Voronoi cells of the positive examples, right? Very simple. Okay? So this is really what is implicitly being represented when I just store a bunch of examples and then use Euclidean distance, right? What I stored is just these dots. But implicitly, I have learned this, let's say, for example, that this was minus, and, this was minus, and this was plus, right? Then the positive region is a very complicated shape, actually, right? It's this thing here. This is actually something much fancier than the decision tree can induce. And yet, it was no trouble whatsoever to induce. Right? Because we never actually bothered to go and figure out the equations of these hyperplanes. God forbid, that would be really expensive. And as it turns out, completely pointless as well, because I can get the same effect just by storing the points and then applying Euclidean distance. Okay? So this is what's really going on when we do nearest neighbor, and it's also why nearest neighbor can be so powerful and yet so simple. Okay? Any questions?
The shape of these regions is so complicated. It seems like you could even have many isolated ones kind of surrounding it, so it seems like overfitting.
Yeah. Very good point, right? So, exactly, you're thinking like a machine learning person. Like, you should be suspicious of this. Whoa, I'm going to get these very jaggedy regions, all sorts of noise, right? This could be a disaster. So, absolutely right. So one of the questions that we're going to ask ourselves is like, how do we combat overfitting? As in every machine learning method, combining overfitting is going to be one of our key preoccupations. And we will talk about that in a little bit, but in the meantime, maybe you can think of what some ways would be of avoiding overfitting. If we don't do anything, indeed, we run a big risk of overfitting.